Alrighty, so our next session for today is called Vision Language Practice, and it will be a lecture presented by Mark Endo. The purpose of this lecture is going to be to try to give you an understanding of when you read a particular paper and you want to understand it from a coder's perspective because you want to build on top of it. How would you go about that actual process? So this is a process that we see time and again needing to be executed really well when it comes to real research settings. So without further ado, I'd like to introduce Mark. Mark, please take it away.
Great, thanks Pranav. Hi everyone. And yeah, I'll be leading this lecture on vision language practice, understanding CXR repair from a coder's perspective. So jumping right into it. After this lecture, you should be comfortable with walking through foreign code bases, and you should also understand the CXR repair code in detail, and lastly, know how to reproduce a paper's results from their code base. So the motivating problem for today is diving into a method called CXR repair and their code base. So suppose that you have an idea for a radiology report generation method that builds upon CXR repair. Now, from a theoretical perspective, let's assume that you know how the CXR repair method works. We'll overview that in a bit, just so you're all familiar. And then at the same time, you're unfamiliar with their code base. So how do you approach diving into a foreign code base and get a better understanding of how their code works? So the agenda for today, first is to just overview the CXR repair method. And then we're going to dive into the README file of the repo. And then lastly, we're going to do a dive into the CXR repair code. So first, I'll just explain some things that I'm using with VS Code debugging with breakpoints. You don't have to use the exact setup that I'm using, but I think it can be helpful if you're looking at code for the first time, or if you're trying to debug something that isn't working the way you think that it should be. Next, we're going to go into the three main files of the repository. So the first would be creating clip embeddings for a corpus of radiology reports. The second file is going to be running through the CXR repair code that will select reports with the highest embedding similarity to image features. And then the third is going to be the evaluation code, specifically looking at the F1 score of the Checkspert embeddings. And we'll get into detail about what those exactly mean in the future slides. All right, so first we're going to do a method overview of the CXR repair method. So to motivate the problem a little bit, we're going to be working with radiology report generation here. So the radiology report represents the sum of the radiologist's highest level of synthesis and insight into a patient's condition. So it's the most important product that radiologists generate to help direct patient care. And going into a little bit about the different sections of the report. So the findings section lists what the radiologist saw in each area of the body in the exam. And the radiologist notes whether they think each area is normal, abnormal, or potentially abnormal. And in the impressions section, which is what we're going to be generating today or retrieving, the radiologist summarizes the findings and reports the most important findings that they see and the possible causes for the findings. This section offers the most important information for decision making. So for today, we're going to be dealing with the impression sections of the reports. All right. So radiology report generation, which aims to automatically generate a free text description for a chest X-ray, in this case, has emerged as a prominent, attractive research direction in both artificial intelligence and clinical medicine. So it can greatly expedite the automation of workflows and improve the quality and standardization of healthcare. So we need to build a model that has both computer vision capabilities to interpret the chest X-ray and also has natural language generation capabilities to write the report, just like a radiologist would. And to achieve that, we can frame this problem as a vision language task. So we'll just quickly go over some trends in vision language learning, which our method here ends up taking use of. So the first is the pre-train and fine-tune paradigm. the focus in vision language models. Second is the transformer architecture has shown great potential across language, vision, and any other unimodal and multimodal tasks. Going onwards, there's been rapid progress in vision language pre-trained models. And then lastly, pre-training data set is usually derived from a natural image text pairs. All right, so for the method that we're working with today, the big idea is that we're gonna be framing it as a retrieval-based chest X-ray report generation method, which means basically let's assume that we have a large corpus of radiology reports written by radiologists describing many different conditions. And now we're given this new chest X-ray image. We'll call it an X-ray image in a test set. So can we find reports, sentences from the corpus of that, the large corpus of the radiology reports previously written that can best describe this new chest X-ray image? And we can use this as our new reports. So we'll turn this into a image text retrieval task. Now, in order to enable a report retrieval system, we need an AI model that knows first how to turn images and reports into vector representations in a multimodal embedding space. And then number two, make sure image and report representations that match well / share the same semantic meaning are mapped into vectors similar to each other. And this is exactly the idea of contrastive learning. So contrastive learning is a machine learning technique used to learn the general vision and language features without labels by teaching the model which image and text pairs are similar or different. All right, and so one example of this is CLIP, which was published by OpenAI in early 2021. And CLIP jointly trained an image encoder and a text encoder to predict the correct pairings of a batch of an image text training example. So yeah, it's demonstrated that the simple pre-training task of predicting which caption goes with which image is an efficient and scalable way to learn state-of-the-art image representations. Now, here's a little bit of the pseudocode of the CLIP model. What we're gonna be working with today will look a little bit like this, where we have, as we can see the top line, we have an image encoder. So we're gonna be encoding some image into some image embedding, and then the text encoder to create some text embedding or text feature. And then we're going to be figuring out the similarity scores or the pairwise cosine similarity between the image and text. And that's done with the logics line. So yeah, we'll go back to code in the future parts of this lecture, but this is just a kind of a flavor of what the model is doing. So how can we adapt this CLIP model to medical AI tasks? So going back to our radiology report generation task, we know that the CLIP pre-trained model can extract high quality features from everyday images. So then we can take inspiration from it and further pre-train it on chest X-ray report pairs. So the model can learn to interpret chest X-rays as well as snap images. So CLIP is quite weak on these several specialized complex or abstract tasks. So we're definitely gonna have to further train it also. All right, so this is the data set that we're going to be using for our pre-training as well as our downstream retrieval task as well. So the Mimic CXR data set is a large publicly available data set on chest X-rays in DICOM format, and you can also have them in JPEG format. And basically, we're going to be using the cosine similarities between each image text representation pair as a measure of how well the reports / sentences from our corpus describe a chest X-ray. And then we can then select the best one to form our predicted report. All right. And then let's just go through the CXR report generation process a little bit. So reports or report sentences from a large corpus are passed through a pre-trained text encoder, and the input chest X-ray is similarly passed through a pre-trained image encoder. And then we can generate a prediction by selecting the report that maximizes similarity between the text and the image embeddings. Or we can select the top case sentences that maximize that similarity. All right, so yeah, there's two approaches here. The first one is we're going to select the report and the training corpus that maximizes the similarity. And the second approach, which we're going to be trying to do today with CXR repair K, is we'll return the top K sentences in the corpus of report sentences that maximizes that score. All right, so this is the final evaluation pipeline. Today, we're going to be trying to reproduce the score of the F1 score. So basically, once we have our ground truth report and our predicted report, we're going to pass it through something called Checkspert, which will create these per pathology labels of whether or not the pathology is present in the chest X-ray. And then from there, we have the 0 and 1 scores for each pathology, and we can run the F1 score. These are just some results from the paper that we are going to be trying to reproduce here. The only score that we're going to be, we don't have too much time, so we're just going to be working on the CXR repair 2 method, which is the top 2 sentences, and we're going to be trying to get this F1 score of 0.256. So yeah, that was it for the theoretical stuff, and we can move over to the code. So I will stop sharing this screen. All right. Let's see if it loaded. All right. Okay, this should work now. All right, so this is the repo of the repository that we're going to be looking at today. So if we look down a bit, we can see that it looks like a fairly standard repository where we have some general overview at the top, a link to the paper if we want to see more about the method itself. But in this case, we'll assume that we have a pretty good fundamental understanding of the model. And then there's different sections for each process. So I'll just briefly run through what each one was. Like if we were to look at it for the first time, or if we are looking at it for the first time, and then we can dive into more sections in greater detail. So the first is just the installation section to get the environment up and running. Oh yes, I can increase the font. Sorry about that. Is that better? Great. All right, so first thing is, yeah, pretty simple. Just it needs PyTorch and a couple other dependencies. So just install PyTorch 1.7.1 or more, and then yeah, there's these other packages that should be installed. And then data processing. So because the Mimic CXR data set isn't, you need to get approval before you can use it. There are some data processing steps that you would have to do because we can't provide the already processed data set. So the first step will be splitting the Mimic data set into a train and a test set. So yeah, this part is pretty standard where we have just one kind of glob together set, and then we need to split it up so we can test on some chest X-ray examples, and then we have the train set, which will have all the corpus of all our reports. So that's the first part of the data processing. The second part is extracting the impression section. So as I said, we're going to be focusing on the impression section of the reports. But before we extract that, we're just given our sort of long format, unorganized, or it is organized, but we're going to have to parse through and grab the impression section out of the whole reports. So that's what this file does. And then going forward, we need to create a test set. So we're going to be creating a H5 file of chest X-rays, which is just a way of storing our chest X-rays in a format that can be easily accessed later in our data set module for PyTorch. And yeah, it's just a pretty efficient way to do it. And then we're also going to be bootstrapping for our test. So because we want confidence intervals in our F1 score, we can have this bootstrapping where we basically will sample indices of the test set when we're evaluating every time. And if we do this over and over again, we can get different scores and then average across to get the mean score, and also take the confidence intervals off of the different scores. So that's how we would do that. And then lastly, we need to get the ground truth labels of test reports. So yeah, we need to get those checks for labels of the ground truth so we can run it through Checkspert to get those. And yeah, that's it for the data processing. Hopefully, if you have time, you can go through each of these files in more detail to get a better understanding of exactly what it's doing. But at a high level, this is what this part's doing. And then now we're on to the main part of the code. So here is the pre-trained clip model. So as we mentioned, the model needs to be trained at some point. So this checkpoint that is provided here is trained on the Mimic CXR train set. And it was also before that pre-trained on natural images and natural image text pairs. So yeah, this can be downloaded here. And yeah, thanks for linking the repo. And yeah, I already have this downloaded in my workspace, but here it is if you would like to download it. And then the first main file is going to be generating the embeddings for the corpus. So we're going to need to get those text embeddings or text encodings for our training corpus. So then we can when it comes time to generate reports, we have access to the whole corpus of embeddings, and we can just very quickly determine which ones are the closest in the embedding space to the image features. So that's what this function is doing. We're going to pass in our clip model path, which we would have downloaded here. This clip pre-trained flag, I think on the note it says, yeah, it signifies that it's first pre-trained on natural image pairs, and then we are training it on the Mimic CXR data set. But if you were to have some checkpoint that didn't follow this, then you would you wouldn't set this flag. And then the data path. So this is the CSV file containing our training corpus, either at the sentence level or report level. So either all of the train corpus sentences or all the train corpus reports, which would have been gotten from the data processing part. So yeah, we have a path for that already done in the workspace. And then this is just where we're going to be saving our embeddings. All right, and then when it comes time to create reports, so now we have all of our trained corpus embedding, it's time to actually generate these reports. So we're going to pass in our embeddings that we just created from before. This is the same clip model path that we had given it when we were creating the embeddings. And then yeah, we have an out directory where we want to save our reports. And then this test CXR path is where our test chest X-ray images are. And then top K means how many sentences are we going to be selecting. And in this case, we want to replicate the CXR repair 2 result. So we'll put into for this. Going a little bit further, we need to generate the labels of our predicted reports. So in order to calculate the F1 score, we need the predicted pathologies for each, the per pathology predictions for the report. So to get that, we can use Checkspert, like we would have done before to create the labels of the ground truth reports. And then lastly, we can test the performance here. So yeah, that's a brief overview of the repo. And yeah, if you're like going through the code and you have questions about arguments or anything, or the way that the workflow is working, then you can always go back to this. But for now, we're going to switch over to the coding part. So I will stop sharing that screen. All right, and then let's see. Can everyone see the code window. All right, great. So this is our workspace that we're going to be working with today. We can see that we have these three files: generate corpus embeddings, run test, and test accuracy batch. And these are the three files that we're going to be going through. So I'm actually going to set, yeah.
Sorry, could you increase the font?
Oh, yes. I think this, is it good now or?
Yeah, it's good.
Okay. Okay, I think I might have to adjust something real quick because I can't see all the text, but 1 second. All right. Okay, this is good. And then I'm actually going to open one more file really quickly. So, okay, yeah, so we have our breakpoints, one on this file, create one here at the start of the file, and then one here at the start of the file. And all right, so the first thing that I'll go over is just some notes on the setup that I'm doing to run this workspace. So I'm using VS Code remotely. So I'm SSHing into a remote server, but at the same time, I do want to do some debugging with breakpoints and everything to kind of, yeah, get a better understanding of what's going on with each line of code. So how I'm doing this is VS Code does have this nice run and debug feature, but you do have to do some quick modifications to make it work for when I'm in this setup. So if you do want to follow this in your launch.json of your VS Code, you can create some configurations that will run certain files. So this configuration will look very similar to the command line argument that we had, where it's generate corpus embeddings.py is the program that we're running. And then, yeah, there's some arguments that I pass in. I go into more detail about this in the notes for the lecture. So if you want to get a better understanding, I definitely highly recommend looking at that. But yeah, this is just kind of showing that I'm not doing exactly what you would regularly do where you input the commands into the terminal. We're doing something a bit different with the debugging feature, and this is how you would set it up. All right, so I'm going to quickly make sure that we're on the right Python interpreter. Yep, that looks right. And then we're going to get started and run our first program here. So this is the generate corpus embeddings, where we're going to take all of our sentences of our mimic CXR train set, and we're going to output the clip embeddings for each of those. We're going to save the clip embeddings for each of those report sentences. So let's start debugging. See what happens. Hopefully there's no issues. Okay, so it looks like we've reached our first breakpoint. I'm going to close this output because it's a lot. All right, so we're here on our first line of our main file. If we just really briefly look through what this file is doing, we see that there's this main that will be called when we make the command, the Python command, or the Python script. We have these arguments in argparse, which we had gone over a bit earlier, and then it does this main call, so main args, and that's exactly where we're stopped right now. So yeah, in this left-hand side, we can see that in our debugger, we get the state of all of our variables, which is pretty nice, I think. So just expanding this a little bit, we can see that like the clip model path is defined here. this is the batch size that we're going to be using. So it would be pretty inefficient to just pass each individual trained sentence into the model like one by one. So we're going to be batching it, sending 2,000 report sentences in at a time. And the text itself is not data intensive, so we can use or not memory intensive, so we can use a pretty high batch size there. If we were working with images, we wouldn't use that high of a batch size. And then, yeah, that's it for the args, or I'll just go over to the next line. And then we have this nice step over, step into, step out of as well that we can make use of when we're debugging here. So yeah, I'll briefly step over this and then go to our next line here. So we can see that this part of the code is where we're going to be loading our model in. So we need to load our clip model in order to pass our sentences into it. So in this case, we are working with a clip pre-trained, where it was first pre-trained on natural images and then further trained on the chest X-ray report pairs. So it's going to break into this if statement, as we can see here. And now we're going to be loading our clip model. So we have this VIT, this vision transformer is what we're going to be using for the encoding of the images. But in this case, we're just going to be working with the text, but we are going to pass that in so we know what kind of clip model we're working with. I'm actually going to step into this function to see what's going on a bit behind the scenes. We're not going to go too much into detail about how this load is working, but as we can see, we are now in our clip.py file. So we've moved files. We are in basically some of the clip setup functions. In this case, we are in the load function. And yeah, it has something where we're downloading, because we're going to have to download the model, and then we're going to have some torch loading going on. I'll just step over a couple of times. This part isn't too important. It's basically just the clip framework that we're going to be loading our model in. So I won't go into too much detail about this. I'll step over a couple of times, but basically it's some torch stuff where we're building our PyTorch model. All right, seems like this slide takes a while. All right, and I'm actually gonna step out just so we can get back. So yeah, once we have our clip model loaded, we can see that it should be in our arguments. How can we make this? Okay, so we can see that our model is a clip model. Context length here is 77. You can check some other variables here as well. But yeah, we will go on. Basically, we have loaded in our clip model, and then now we need to load in the weights of our pre-trained checkpoints. So let's go ahead and do that. I'll just step over this. Alrighty, and lastly, let's move it on to the GPU in this case, because our device is CUDA. All right, so now we have our model loaded in, and it's time to get working on getting our impressions ready to be passed into the model. So first thing that we're going to do here is read in our CSV that contains all of the corpus sentences. So let's do that. All right, so now we should have this impressions. This is a data frame here, or let's see what we have. I won't go too far into here, but yeah, basically we see our values. We do have an array of different report sentences. It looks like the first one here starts with no acute pulmonary, So we have our reports. There's going to be a lot of them. We can see the size is around 780,000 report sentences. So that's going to be a lot, but yeah, each one we have it in the text format right now. So let's step over a couple more times. And we can see now we're working on our batching. So we're going to be sending our report sentences into our model in batches. It looks like this code is just doing some of the logic behind what the batching process will be like. So yeah, now we're finally into iterating through our data set. Here we have batch, which will take a subset of the impressions. Yeah, we do some indexing here. And let's just check out what the batch is. So yeah, we can see that the 0th index in the batch contains, it's cut up on us here right now, but it looks like the same thing from before because we're on the first batch. No acute pulmonary, and then it continues onwards. So that is our batch, and now we're going to have to encode the text. So let's step into this function, and this is going to be the main function where we are getting our text embeddings from the impression sentences. All right, so this function is actually in the same file. As we can see, we have our impressions that we passed in, our clip model, as well as the device that we're running on. So let's step a couple more times. We have our impressions. I guess we're calling them trimmed impressions. And then first thing that we're going to have to do is tokenize our impressions. Since the model you can't just pass in text directly, we're going to have to tokenize them to make them in a usable format for our clip model. So let's step into this. I don't think the tokenize will be too specific to this program. I think we're just going to be using a basic tokenizer here, it looks like. But yeah, I won't go into too much detail, but we have our tokenize function, which it looks like we have the start of text token, end of text token, and we're going to be, all of our tokens will be this, we'll start with the start token, and then we'll get some tokens of our text, and then we'll end with the end token. If we would want to, if we would want to see what this encode is doing with our text to see actually how the tokenizing process is working, we can step into this as well. And we can see exactly how our tokenized process is working. But I'm going to step out of this because it's not too important for this method that we're working on. I think it's a pretty standard tokenizing process. All right. So once we have all of our tokenized input, I'm going to step out of this again because it's going to do some more logic with the tokenizing. But once we have that, let's see, we're still in the clip.py file. All right, so now we are back. We have, once I step over, we should have our impression tokens. So all of the tokenized versions of our input. And as we can see here, we have our tensor. It looks like a 2D tensor. We can check the shape of our tensor to make sure it makes sense. So yeah, our size is 2000. So we had a batch size of 2000 reports, and our second dimension is 77. So this is, I think before we looked at the context length was 77. So basically our input can be up to 77 words, and it should be padded at the end. So if we look at our data, let me see. So yeah, we can see at the end indices, it looks to be padded to the end. But yeah, that is our tokenized input. And then now we're going to be doing our model.encode text. So this is the main function where our clip model will take in our tokenized version of our sentences and embed them into the clip embedding space. So let's step into this and see what's going on here. So now we're in our, let's see, what file are we in? We're in our model.py file, which is basically all of the model part of the clip. So we have, if we just scroll around very briefly, we have a bunch of different models. This is a ResNet, which would probably be used for the vision encoder if we were to use a ResNet instead of a vision transformer. Yeah, a bunch of different models. We don't need to go over all of these, but we're right here in our encode text function. where we have, we basically are passing this through our model where we have positional embeddings. We're going to run it through a transformer, do some final looks like our final layer, and then we're going to be just ending up returning our outputted clip embeddings. So I will actually step out of this, but yeah, this is what the model is doing to our text in order to get our clip embeddings. This might take a little bit of time. Okay, so now we should have our clip embeddings. And just to sanity check everything, we can check our shape of our embeddings. So our embeddings should still have 2000 on the first dimension because we still should have 2000 examples in our batch, but our second dimension should be the shape of our clip embedding dimension size. So yeah, we can see here, we still have 2000, but instead of 77, which was the context length of each sentence, now it's 512, which is the clip embedding dimension. So basically every sentence has been transformed into a embedding of size 512. All right, and then going forward, we can step over again. So now we've just normalized our text embeddings and we can finally return them. So yeah, this is looking pretty good. We have our weights, which is our clip text embeddings. We can append them to some tensors. So it looks like this tensors array is just storing all of our outputted text embeddings. And yeah, it looks like we're gonna be doing this in a for loop. Let's see if I can get my output back. All right, so I'm actually gonna let this run for a little bit just to see the output. So okay, it looks like it's not going to show us the progress bar because there's something with this. It's hiding something, but basically it's just going through in each batch. It's taking the impressions for each batch. It's passing the tokenized version into our clip model, saving the weights to our tensors list. I'll stop it real quick. And once we're done with all of that, we can take just concat all of our different saved embeddings together into our clip embeddings. And then finally, it looks like we're going to be saving this to our files. So we have our impressions, which is the text version, as well as our embeddings that we created of them. And yeah, we'll save it into this corpus embeddings directory, and then we'll have some out paths. So if we look in our files here, since I already ran this, I should already have this corpus embeddings directory, and I have these pre-trained clip embeddings, text embeddings that we can use in the next file. So yeah, that was it for this file. I will switch over to the next one. I'm gonna interrupt this. Alrighty, so now we're done generating our corpus embeddings. Everything went smoothly there, and now we can go on to generating our reports. So this is, I'm actually going to close some of the files here that were opened up from our debugger. All right, so now we're on to our run test file, and I'll close or minimize this output for now. And yeah, we're going to set a breakpoint when our main function is called. I think again, there's going to be some arg parsing done here where we take in all of our arguments, but we'll just skip past that. If we want to see what any of the values are, we'll have them in our variables states over on our left-hand side. But yeah, let's run this. Okay, that was quick. So I think the first part of this file is going to look pretty similar to the first file where we are loading in our clip model. So I'm going to step over these parts. Basically, yeah, we can see we have our model, same as before. I won't step into it again. All right, we're loading our pre-trained weights into the model. And yeah, now we have our model ready to go. So once we've done that, we can then load in our corpus embeddings, which we just created. So here we're just getting the path it looks like, and we're going to be calling this get text embeddings, which should grab our saved corpus embeddings for us. I'll step into this, see what's going on here. I think it looks like a simple torch.load where we're loading in the path. So yeah, that's getting our impressions in the text format as well as the clip embeddings of the text. So it's got it for us. We can check the shapes of our different, move this down. We can check the shapes of our embeddings to make sure they're what we had before, just a sanity check. I think I skipped over. Oh yeah, so here's the shape. So now we have for our around 780,000 train set sentences or train corpus sentences, we have a clip embedding of dimension 512. So that's looking great. And we have our raw impressions as well, which will have the corresponding text for each sentence. So let's go down. It looks like there's this part where it's if there's a correlations path, we'll do something different. I think this is used if you would want to select a subset of the training corpus to retrieve from. In this case, we're not going to do that. I believe this was done in the aberrations portion of that paper. But yeah, in this case, we're not going to do that. But if we wanted to, we could provide some correlations path that looks like, which will take a selected indices that we would want to be able to use in our training corpus. But yeah, I think that's about it for this function. It just looks like we're going to return our impressions and our clip embeddings. And now we're on to the next section. So this is, we're going to be loading in our Mimic CXR chest X-ray data set. So we can step into this data set here. And we can see we are in our data directory Mimic image data set file. So this is going to be the file where we're going to be loading in our test images or our chest X-rays. And if we look at our call here, we have our self.image data set. So this is going to contain all of the test images. In this case, we're using an H5 file in order to store these. This was done in our data processing. And this is just going to make it efficient when we want to load our images in. And yeah, we have a couple other things. This all looks fairly standard for a PyTorch vision data set. We have some normalize function, which we're going to apply to each of the chest X-rays. If close pre-trained. So it looks like we have this if else. I think basically if we are using this format that we currently are, our clip model is expecting a input resolution of 224. So we're gonna have to resize each of the images. So that's what this is doing. And then our transform is gonna be composed of our normalizing for the mean and standard deviation, as well as our resizing to our size 224 image that we want. So I think that's about it for our data set. We can quickly look at the get item to see exactly what it looks like in order to get a test set image, but it looks fairly standard. So we have our image data set, which was our H5 file here that we loaded in, and then we're going to index the image that we want. It's going to be 320 by 320. And then, we're just going to expand it to the format we want, where I think, yeah, we're gonna copy in the channels because we're working with a black and white image, so we don't have color here. And yeah, final things, we're just gonna convert it to a NumPy, and then we're gonna perform our transform function, which above was the normalizing and the resizing. So our final output should be of resolution 224. All right, I will step over these, and yeah, it looks like we have created our mimic image data set, called it data set or dset, and then now we have our data loader. This looks like a very standard data loader. We're not doing anything custom here. This is just the Torch utils data one. And then we have this function which is called predict. So this is going to be the important function here. Let's step into this and see what's going on. So we have our loader, which contains the data loader of our test images, our text embeddings of all of the training corpus, model device we're running on, and then top K is how many sentences we want to retrieve. So we have this predicted corpus indices, torch.zeros. It looks like this is going to be where we're storing our top K sentences for each of the test images. So let's step over this, and we'll see where we're going to be adding to this. Actually, if we highlight it, we can see exactly where we're going to be adding to it. But yeah, let's continue on. So we're going to be iterating through our data loader of test images. Very quickly, I'll go over one more time. So we have our images variable that we can look at. Let's check the shape of this, see what we're working with. So yeah, the shape is 4 by 3 by 224 by 224. So it looks like our batch size is going to be 4. So at each step, we're going to be processing 4 test set images. 3 is the number of channels in each image, and then it's a 224 by 224 image. So that's looking good. That makes sense. And then we're going to be calling our encode image function on this batch of images. So let's step into this and see what's going on. This, we can step in again and see exactly what is being called. All right, okay, yeah, it seemed like it was a bit hard to step into, but basically it's being passed into our clip vision encoder in order to get our image features. And now it's going to do some normalizing, and we can see what our image features shape is. So let's close out of images. Let's go into image features. And let's see if this makes sense. I think I passed it. Okay, so the shape is 4. So yeah, we have our batch size of 4, where each batch we're processing 4 test set images, and then 512 is the clip embedding space size. So this is looking good. And then we have this logits. We're setting this logits variable here, and yeah, this is going to be basically the cosine similarity between the image features and the text embeddings. And this is going to look fairly similar to that pseudocode that we were looking at earlier, where we're calculating the similarities between the image features in the embedding space and the text embeddings in the embedding space. So that is going to give us the similarity scores for each test set image in the batch, and then for every training set sentence in our corpus. So this is going to be probably a pretty big size tensor. So if we look, we don't have to check the shapes every time, but just as a sanity check, let's look at our logits and see what we're working with. So yeah, we're going to have for each test set image, it looks like we have 4, which is our batch size. We're going to have around 780,000 similarity scores. So for each training set sentence example, how similar is it to the 4 test set images that we're currently processing? Alrighty, and then from here, it looks like we're going to be doing this arg sorting. So we don't just want the similarity scores, we want to know which train set examples are the most similar. So we're going to arg sort it in order to get the top K most similar reports. So let's step over. So now our size should have shrunk considerably, where we should no longer have 780,000 examples. Instead, we have just the top 2 indices in our training corpus. So yeah, that is looking good. Let's go forward a bit. So yeah, it looks like here we're going to be saving our top train indices into this torch tensor. And it's going to be doing this in batches. So it's going to loop a bunch of times. I'm letting it play a bit. I don't think we're going to let it finish because we've already loaded in the torch embedding or the clip embeddings for our training corpus. We see that it's actually running relatively quickly. It's going to take like a minute or so to do all of the test set images, but I will stop it here and then we can see what's going to happen after we call our predict file. So we don't have the breakpoints anymore to help guide us, but we have this ypred, which is all of the top K indices for each test set example. And then it looks like we're going to be saving our reports. So right now we just have the indices of our train set, but we're going to have to convert that to the actual generated reports. So we'll see how that's being done in our save reports file, where we have, let's see. So for each of our different examples in the test set, we're going to be creating the report by taking our raw impressions. So this was the list of all of the different train set sentences or the training corpus sentences. And then for each of our top K predictions, we're going to append the training corpus example that corresponds to that. So yeah, that looks like that's about it for this function. And it will save it to our out path, which I've already run this file. So I should have it in our CXR repair 2 mimic results. It should be our generator reports.csv file. So I will stop this code. And we're going to move on to our next file. Looks like we have 8 minutes. Should be enough time. All right. And as an intermediate step, if we would want to calculate the F1 score, which we are going to do now, we're going to have to get the per pathology labels of our generator reports. So we're going to have to run these reports through Checkspurt, which is, yeah, it's another code repo that you'd have to get some familiarity with. I think it's actually fairly easy just to run it without looking at the code. They made it, yeah, a pretty simple process, just having reports and generating these per pathology predictions, which is really cool. But yeah, in this case, I've already done that processing here. And now we can move on to our test batch file. So I'm going to go to our debugger, batch, and we'll run this one. Alrighty, so it looks like, okay, so we've reached our breakpoint here. Going through the file a little bit, we have our same argparse setup, and then we're going to be calling this bootstrap F1 score. So let's see exactly what's going on here. Our data set isn't going to be Checkspurt in this case, so it won't break into that. And the first thing we're going to do is load in our true labels. So this is the per pathology labels of our test set reports. So let's step over that. And this was already created by running Checkspurt on our ground truth test set reports. And then we're going to do something very similar for our predicted labels. So these are the labels that we had just created based off of our generated reports if we were to have run our file through Checkspert. And once we have this, we're just going to create NumPy arrays from these data frames. And then we have, I think this, it looks like we're just everything that's set to -1, which means that the label's uncertain. So it might or might not be a pathology. The pathology would be there. We're just going to set these to 0. And then let's check out the shape since we have our nice debugger here. So shape is 3,678. So that's how many test set examples we're working with. And 14 is the per pathology labels. So yeah, I think here are labels. There should be 14 of these. All right, so let's continue forward and let's check out what's going on. So for 10 bootstraps, so as I said before, in this case, we're not just going to run the S1 score of the whole test set once. We're going to sample indices of the test set and run it however many times we want. And then we can get these multiple scores that we can take the mean of, or we can also get the confidence intervals based off of that. So for each of these different bootstraps, basically, we're going to load in which indices of the test set we want to actually test on. And then we're going to call this F1 badge score. So I'll step into this function. I think this F1 score, if we trace what this is, we're just using sklearn's F1 score, passing in our true labels and our predicted labels. And then we're going to use the F1 macro score. It looks like here we are indexing our indices. So again, we don't want to take just the whole test set. We want to take specific indices. In this case, I think we are resampling, or we're sampling, the test and the test set and times where n is the number of our test set. And we're resampling with replacements. So we're not just getting the test set in completion every time. So yeah, that's going to be our F1 score. We can check what our F1 score is for this bootstrap. It looks like it's 0.252. And then we can just let this thing keep on running. So I'll just let it run. It's going to be doing this 10 times. And I think it's already completed. So we can see below, there was a line where it prints our F1 score. So let's just see. So once we've added up all the scores into our scores list, we can then take the interval. This logic here, it looks like it's just to get our confidence intervals and our mean. So, and then we're going to print it out. So it looks like we got the F1 mean of 0.254 and then plus or minus 0.00004. So yeah, that was it for all of our functions. And that was the last file as well. So yeah, hopefully going through all of these files with the debugger, you learned a good way to trace through code that you're unfamiliar with and be able to reproduce results from a paper. Thank you so much for listening.
Thank you so much, Mark, for the wonderful code walkthroughs of how to go about looking at the code for a new paper. Thank you.
Yeah,